thanks so much for inviting me, and yeah, I'm very excited to be here. What fascinates me about computer vision is that, and machine learning in general, is that the hardest problems are the ones that are easiest for us. And so, if you've ever had a VCR, and maybe I don't know, maybe younger guys have not had a VCR. If you ever had a VCR and you watched a video, maybe on YouTube, and you watch a video and all of a sudden the color just drops out, right? You're faced with this question that is obvious to all of us. We really don't have to think about this question. Is in this frame where the color has been removed, what color is that pixel? Red, right? It's not a trick question, right? It would be very surprising if that balloon all of a sudden became green all of a sudden, right? And so this is an example of a question that is just obvious to us. And the reason why we know this is because we understand the general principle that there's this temporal coherence to color. The color of objects around us spontaneously change over time, right? If this boy's shirt changed all of a sudden, or the medicine here that the person was putting on their finger changed color all of a sudden, this would be very surprising. And there's obviously exceptions to this rule, right? There's any exceptions. So you turn on a green light, and all of a sudden the colors are going to change, right? There's various well-known illusions, right? Who's seen this illusion before? Okay, most of you know what this is, right? And various illusions, right? Red, color ready is red, right? So I still can only see blue. I can't see anything else besides blue. But kind of just in general, you know, okay, with these exceptions in mind, if you just take random videos from the web, generally the color is going to be temporally coherent and it's going to be stable. So it's probably not going to change over time. And so, kind of in a paper that we wrote about a year ago now, we were interested in using this clue of the coherence of the color as a way to do self-supervised tracking. And that if you can train a model to colorize a video that you remove the color, but you have one frame that you do have color, by training it to fill in the colors here, can we show that tracking is going to emerge in a self-supervised way? And I think this is an exciting question because there's been so much progress in computer vision machine learning over the last 5 years or so, and basically supervised learning, labeled data has been driving that progress. But we can't label our way through all these problems, right? We need to develop approaches that learn on their own. Eric here has done some great work on instruction, and I think this is a key problem in the field is how do you just create these machines that learn on their own without requiring a human in the loop at every step of the way. Okay, so we're able to just collect huge amounts of video from the web. It doesn't have any labels, but the color is going to be coherent across time, right? And kind of the hypothesis here is that that's going to be an excellent self-supervised signal to learn to track. We've done just this is kind of building off of some work that I did during my Ph.D., which was trying to use unlabeled video to predict what's going to happen next. And so we've done some various things on this before, just a quick recap on, for example, building generative models of video that just given large amounts of video try to generate videos out in the future, actually extrapolate the videos into the short-term future. This is trying to generate videos that are about 1.5 seconds long in terms of beaches, golf courses, train stations. The press got really freaked out by these three-eyed babies. I think this is back in 2016, so I think the latest and greatest in GANs could probably do much better than this. But this is there's actually a lot of interesting examples here where the mistakes it make are just things that are obvious to us, but they're very challenging for machine learning. example where the train pulls away from the train station, but it's still there once it leaves, right? This is something that is obvious, it's intuitive, it's a type of common sense, right? A bit of common sense, right? Okay, so beyond just generating videos, we've also done things in prediction in terms of, because video basically gives you time for free, right? This temporal order of frames is basically baked into the modality. You can do this for a lot of different tasks. You can also try to predict action. So here's an older result of, for example, people are about to hug, and they do hug. The problem's pretty challenging. It's not always easy to predict. So we get it wrong. But okay, but in general, what I love about these videos is essentially we can amass this huge collection of boring home movies, right? And I don't really know why people upload these things. It's very chaotic. It's unconstrained. There's a lot of noise. But we get a lot of them, and they're going to show us the vast diversity and the complexity of the visual world at scale, right? And they tell us how objects are going to move through the scene, what different scenes afford, and there's multiple modalities here. So there's also sound and speech, right? Dig into this, and so kind of the theme of my research group here is how do we take advantage of this huge resource and all this vast context in order to learn perception without a human teacher. And so this first part of the talk, I want to focus on the colorization aspect here about how the color is moving temporally through this big table. And colorization really is not, we're not the first person to think about colorization. There's been a variety of work in the last few years that focuses on colorization, in particular for images. Here's one fairly impressive result of doing colorization from the Berkeley group, where given a black and white photo from Ansel Adams, they train a neural net to predict the color, which you can do for free because most color photographs today have color. And here's the automatic colorization of that. And it does a pretty good job. It's learned pretty useful priors here about typically foliage is going to be green, water is going to be blue. So most of this prior work has asked this question of, given a grayscale photo, what color is each pixel? We're going to ask a different question here. We're going to say in video, where should you copy the color from? So rather than synthesizing colors from scratch, we want to colorize a video frame by copying it from somewhere in a previous frame. Okay, and so just to drive this point home, we can play a little game. Let's see, get my cursor to show up. Okay, so the game here is that I'm going to move my cursor around, and I want you to clap when the cursor is on top of the region where we're going to copy the color from. Okay, right? So we want to predict what color should be there, right? And you don't know, because it's a shirt. It could be in any color. People are wearing a variety of different shirts here, right? So we cannot synthesize that color from scratch, right? Basically, it's a uniform distribution of colors. But instead, we're going to say, where in this image would I grab that same color? It should be really obvious to you, right? Hopefully. So as I move it around, right, remember, I guess let's do a warm-up round just to solve. 1, 2, 3. So warm round, okay. So when it's over the right region, right, is when you should clap, right? Okay, good. You all can track objects, right? But actually, right, here's what here's where the colors are, right? And even though no one wanted to get lucky, right? How embarrassing would it have been to clap there, right? You would have been right? But you could have been wrong, right? And so this is an important point about this task of when you want to colorize the frame here, where should you grab the colors from, right? You want to be robust to outliers, right? You don't want to just be clustering based off of low clues like a color, because then you might think that this towel will actually morph into the shirt, right? And so this is an important point to keep in mind when we talk about the exact method. You want to be robust to these types of outliers. Okay. So here's another example. We're going to predict the color for this person's shirt. But here something has changed because there's a self-occlusion, right? We actually can't see the front of the shirt anymore in the reference frame. And so I think this is one thing that's interesting about color just compared to traditional optic flow is that the coarseness of it does impose useful priors, and it actually be robust to occlusion, right? It encodes this natural prior that typically the color of objects is going to be the same around as the object does out of plane rotation. Okay, so the exact approach we're going to take here is we're essentially going to train a neural net, no surprise there, to do this colorization task. And the way this works is we input a reference frame, or sorry, an input frame in grayscale. And we're going to train a neural net that takes in this grayscale frame and learns to point into a reference frame. And it's going to train it such that it's going to point to the right place, that it can essentially copy and paste the color back into the target. Right? So you're learning to copy and paste colors across time. And the reason why we can do this in a self-supervised way is because we know what the ground truth color is here, right? And so this provides a loss in order to train a model to do this colorization task. And the hypothesis is that even though this is kind of a roundabout way of doing colorization, what we expect and what experiments are going to show is that this is going to, the way it has to solve this task is by tracking the objects. Right? And this is going to force the model to learn in a self-supervised way to track the object. Okay, so the way we do this with a neural net is really simple. We're going to put a convolutional net on top of each frame here, and we can think about. We talk about the embedding that comes out from this convolutional net at each kind of patch in the window as Fj and Fi, right? And so we can build over the convolutional net on both frames. And then we're going to have a similarity metric between embeddings in the reference frame and embeddings in the input frame, which we'll write as Aij, right? Aij is going to be a learned embedding matrix that tells us how similar is patch I to patch J. And we're essentially just going to use a similarity metric that's an inner product normalized by softmax. It's also to the neural network nomenclature is what you might call the attention to. Right? And so what this mechanism do is encode how similar in grayscale are these points going to be. The embedding space here, F, is going to be learned from scratch. Okay. So then what we want to do is we want to predict. We want to use this similarity matrix to predict what the color is for patch J here, which we'll write as C hat J. Right? And we're just going to write that as a linear combination of all the colors in the reference frame weighted by the similarity matrix Aij. Okay? So CI is going to be a color in the reference frame, and C hat J is going to be a weighted combination of all these for the target frame weighted by Aij. Okay, so that's what the prediction is, right, for the color is going to be. And then in training, it's very simple just to train this because we know what the ground truth Cj is, and so we can just write down a loss function where our prediction of this weighted combination must match the true Cj under some loss function. And so you can do fitting loss, you can do cross entropy loss, whatever loss function you want, and just train this up. And because you can backprop through this entire process, you can learn embeddings, right, such that such that when you take away the combination of the reference colors, you will cover the target color here. Okay. So one important point about this formulation is it's not enforcing windows that have the same color to lie in the same point in embedding space. Right? Remember, none of us wanted to be embarrassed and clap on the towel, right? And what this formation relaxes here, it's not just doing naive clustering on color, it's training the model saying you have to recover the color here, and you can grab colors from anywhere here, right? So there's kind of this robustness in the way it's baked in. Yes?
You're probably going to address this, but if you have a texture pattern,
yes,
then it seems like the color of the central pixel could change very rapidly, even while the similarity function is not changing rapidly. So why don't you get blending? Like if you have a red and green checkered surface, why doesn't it come out brown or yellow? Because it's an average.
Because we're trying to do this per pixel. So even if that texture pattern moves, it still should predict the colors for that texture.
But isn't your final color that you map a linear combination of things according to their similarity?
That's right. That's right. I see what you're saying. So if you had, for example, in this person's shirt, say that the texture pattern, the texture is the same in here, but the color could change between the left, and the right. I think that's your.
Just across, the color could change dramatically from one pixel to the next, whereas the patch being used to determine the similarity could be quite different.
The patch.
That's right. The patches could have very similarity, whereas the central pixel that you're. I would just think it would blend nearby colors.
Well, so because you're training it to actually recover the true color and not the blended one, it won't learn to blend.
I hear what you're saying. I just don't understand how it's able to avoid that. But
well, so what happens is this AIJ. If this AIJ is if you think of AJ here being a distribution over all the colors here, which color should you grab, right? If that is a uniform distribution, then the predicted color will just be the average of all of the colors.
right.
Here.
So I'm just saying, if you had two pixels next to each other, one red and one green, and they're surrounded by something that looks exactly like the patch over here, you want to put 50% of it on red and 50% on green, and thus get a mixed color.
If you had that exact scenario, yes. But I think this is what I'm talking about. In the real world,
but like the carpet here, for example, how would you get the right color out of the carpet? Because wouldn't it blend all those colors?
Well, so it depends on the contextual window for what the receptive field of this embedding is. If you're right, if you have a small window, you can see a small part, and the texture between here and here is going to be the same, right? Then you're right, this is going to be confused. But in practice, you can make this receptive field quite large, and then there's actually a lot of interesting points, right, that you can still use to track the color, right? So this model could learn, right, that this larger texture here, right, between these two lines, that is distinctive for this blue color, right? And then this other patch that has a different texture here at a larger scale is distinctive. Well, yeah.
So, in this example, wouldn't just paste the texture which it copies from the reference frame, because I guess these are still very uniform colors, but if you look at this texture, this is much more like random noise. And would it like paste from them, or would it like color each pixel separately and then you could get something really weird out?
Yeah, so it's solving this problem for each pixel. Excuse me. I guess you could say independently, although the receptive fields of each embedding does overlap. So in this case, where the texture does change, this would actually be pretty easy for the system to solve this, the model to solve all this, because the actual
Right.
embeddings will be quite
We're talking about the case where you've got 10 different colors in the same texture.
right.
And the
right.
difference in the similarity function between one color and another will be almost imperceptible. That's what we're talking
Right,
about.
right. No, I understand. And so, but if you make the receptive field of the magnetic space much larger, right? I think that resolves this ambiguity.
So maybe you'll discuss this later, but what if I trained AIJ to be equal to optical flow? Would you get the same thing, or is this?
Oh, yeah, you could train this to be equivalent to optic flow. I guess that would require, one that would require some ground truth of what the flow is. The other one is that this would not, and so we'll show the results. What's interesting about this is that it can be robust to cases where optic flow is not all the time. So you have an out-of-plane rotation,
Right.
right? How do you try to, there's no valid flow.
But sort of qualitatively, do you get that, or?
Yeah, qualitatively it does work in terms of there's that out-of-plane rotation, or you have very non-rigid motion. We have some examples where you scramble eggs, right? And there it does. It's very hard to estimate flow there. Okay. Okay. So just kind of as an aside. So the way color film was originally made, and it's kind of, I guess, a baseline from 1902, the way the color film was originally made was you took a video in black and white, and then there was basically original color film was produced in a sweat house, kind of like mechanical turk, but not with computers, where people would go through the film and actually literally just paint on top of the film. And this is how the very first color films were made. So this job was pretty intensive because you had to paint the object between each adjacent frame to be the same. You had to paint the object in each frame to be the same color. And if you didn't do that right, the results look quite unusual. So here is one of the very first color films that was produced this way. This is in 1995. So all of a sudden it turns into color, right? And so you get these very cool effects, right? Where each frame is painted independently, right? And so it's kind of, anyways, I want to make this connection here about colorization, where if you mess this up, right, it was quite unusual. Okay, so here are some examples of the colorization model, where it's trained on the colorization task. This frame is the reference frame that's provided, so it receives the color for this frame. And this is the video in grayscale that's fed in, and these are the colors that are predicted for that frame. So you can train this up on basically as big a data set as you want, right? And then you just evaluate these on the videos that's not seen before. I think it does a pretty good job. So here's the egg example. This would be a case where it's very hard to estimate flow. Right? This is a non-rigid motion. And so it actually does a pretty good job at propagating that color there. One failure here is when this person dances, the legs don't get colorized right. And the reason for that is because you don't see the legs in the reference frame, right? And so this causes a mistake. And so kind of what's interesting empirically about this is that you could actually recover the colors. We had this prior, we assume that the legs are going to be the same color as the hand, right? This would be a reasonable prior to learn, so why doesn't it learn that? And I guess what's interesting is it's actually learning a much, we'll see results of this later, where it learns a pretty fine point-to-point correspondence. Okay, so here's some more examples of the colorization. This is just what task that it's trained for. So I love the butter spreading the toast, because again, there's no real flow field that's fine line there. But it does a reasonable job at actually predicting the colors or the kid going on the water. Yeah, sorry.
Are we using the reference frame for all the subsequent predictions?
That's right.
Okay.
Okay, yeah. So there's two different ways you could do this in video. So if you have a grayscale video, you could always copy from the reference frame, or you could copy from the previous frame, right? And if you copy from the previous frame, the challenge is there's going to be drift, right? If you make a mistake, then you're committed to that mistake. I actually can't remember which one we used at the end of the day.
Yeah, that's what I wanted to know.
Yeah. But it's a typical trade-off in okay, so coherenzation I think is an interesting task itself, but I think what's particularly exciting is that just by training it to do this coherenzation task, tracking emerges on its own. And essentially what happens is that this pointing mechanism acts as a tracker, right? And we can reuse the same model for coherenzation, but now use it for tracking. And the kind of, I guess, conceptually the way you use this for tracking is very simple. Before you trained it to propagate colors into the future frames, now we're just going to change this so it can propagate a segmentation mask into the future. Right? So we run the same model, but now instead of propagating color channels, we propagate a vector corresponding to this segmentation. Okay, and the reason why this works is that the final predictions from the model C hat J, that is just because it's just a linear combination of all the CIs in the reference frame. This is non-parametric, so you can actually change the dimensionality of C between training and test. Right? So even though in training CI is to represent color with two dimensions, we can now change the meaning of C to be a binary mass instead. Yeah.
So when you train this, you can pick a distance between the reference frame and the subsequent frame, and you could have that always be one frame, or you could have it be a mixture of longer time steps. And what do you use? I would think if you wanted the optimum tracking, you would want the difference between the reference and the predicted frame to always be one, because then you're really focused on what the immediate future looks like.
Well, so yeah, I think one typical challenge in tracking is when you go longer term, because the appearance is going to change more. So the way this is trained is it's actually over different time scales of one. So it's the way you construct this is it's both doing frames that are purely close to each other, say half a second frame apart, but also could be 10 seconds out in the future.
And that actually helps your tracking. Why do you think that helps tracking, since in tracking you're usually trying to go from previous frame to the frame T+1?
I think it goes back to this question of drift, because if you make a mistake at the short time period, and you get committed to that, you can't recover from that. Well, if you look at longer term relationships, you have a chance to recover. Right? You could have, for example, you could have periodic motion where during the immediate frame is actually there's been occlusion, so it's very hard to do tracking, but when it reappears, right, you can block in and correctly track the object. Yeah.
Do you have the ground truth segmentation mask for this?
Yes, that's a good point. So this is trained with just unlabeled video, but then at test time, you need a single label to say what object do you want to track. You have to specify. This is not a self-starting tracker, so you have to specify what region of interest that you want to track.
I mean, what is the loss in the end? I mean, there's no ground truth, right? Ground truth, right?
For the tracking.
Yeah.
So in the tracking, this is not trained. We don't train it on the tracking task. So we don't need ground truth. We need ground truth for evaluation, which we have. But for training, you don't need ground truth. It's not trained on.
But this is something similar similar that mask CNN does, right? I mean, through various frames, across frames.
What do you mean?
I mean, mask CNN can do a similar thing, right? Across frames, segment out the object.
I think mask tracing is typically for an image, no? So, right, so, actually I don't understand the question.
So, yeah, maybe you can talk about it later. But I had a related question to the first one I asked, which was, if this was the task I cared about,
Yeah.
how does optic flow prediction compare?
Oh, yeah, well, we'll show that, yeah. Okay. Once the results all. Critical, good. Yeah.
So I understand the way I understand it is that Fi and Fj are gonna give you the spatial similarities in those two frames, and searching through different CIs is gonna give you the more accurate information about the color.
Searching, yeah.
Right. So what I'm getting at is that the correspondence need not be very good as you would want it to be for segmentation,
Yes.
because a different part of my shirt could give me very good information about the color, still have good spatial, and it could mismatch, like give worse results on this stuff. So
I think it depends on the task. If you want accurate point-to-point correspondence, this is probably not the right approach, right? Because one example is that if you want to copy the colors from my shirt, there's many different regions you can copy that from.
Yeah.
Right. But at the same time, point-to-point correspondence is very hard, and it's not always possible to calculate that point-to-point correspondence, right? And in those situations, if I turn or there's large depth of information, then you want to relax that point-to-point correspondence. Okay, so here's some. So the point here is that it's trained on this correlation task. In some sense, and it's never seen a tracking task. And the only label that you have to provide it at the end of the day is just what is the region of interest you want to track in the first frame, some segmentation. Okay. So we evaluated this on the Davis data set, and this is a it's a very challenging data set where in video multiple objects are segmented across time. And at the time, this was the state-of-the-art data set for video segmentation. Here are some results of the tracking where it only got to see the labels for the first frame, and it's using this model to propagate those segmentations into the future. And so I think it actually does a pretty good job considering it's never trained on tracking. So here's a good example where the ball undergoes a partial occlusion, still tracks the ball through it. These are challenging cases because the coats, the lab coats that they wear and the uniforms are the same color, right? Both people here are, so this is orange and red as a children. Both people wearing the same colored coat, but it actually is able to separate their identities, right? And this goes back to this point because this model is not enforcing that all colors have to lie in the same space. Right? Yeah.
I guess one drawback is you don't get to see color.
That's right. That's right. That's right.
So it would be very easy if you could see color.
That's right. I think that's what's interesting. So right. So yeah, if I'm wearing a red shirt and I'm walking in a crowd, that's a very good discriminative clue to track, right? But then at the same time, if that's such a good clue, it's actually a good clue to train it too, right? So yeah.
Well, couldn't you extend your system to also have a sort of a runtime loss term to match colors as you go?
Sorry, you could do that.
Right, I mean,
yeah.
if your solution seems to be skipping around the colors.
That's right. That's right. If you wanted the best, I mean, you can improve upon this, and of course, if you want the best tracking performance, you can definitely include color. Okay, here's some more examples. So here's an example where it doesn't, where there's a full occlusion and it doesn't recover. And so this kind of goes back actually to this re-identification problem or object permanence. Once an object leaves view, how do you know this still exists, right? It hasn't, because there's no memory built into the model, it's not able to resolve that. Okay, one thing that's interesting is that we can do this for a variety of different tracking tasks. So we can also do this for pose tracking. And this is a task that requires much finer point-to-point correspondence, right? So previously, right, it didn't require very accurate point-to-point correspondence. Pose does require, it's still not going to be pixel perfect, but it requires more fine resolution. And so the way this works is each human joint in the first frame is specified, and then you just warp it according to this model. And it does a pretty good job, I think. So it's not state of the art, right? If you want the best performance at post-truth tracking, supervised data is the way to go, right? But that's not really the point here. The point was, can you do this in a self-supervised way? Okay, so again, just run onto this question, how does this compare to optical flow? So we can evaluate this in terms of what the performance is on the Davis data set versus how far out from the initial frame you've gone. So if you just, naive baseline is just you assume that the video is stationary, and that the first frame is not going to change. So that, of course, drops off. If you use FlowNet, and then you warp it, you get this orange curve here. So it looks like that. It does better than sort of this naive baseline. And then if you include, if you do colorization instead and compare against that optic flow, it does slightly better than just using FlowNet.
So I have a sort of I feel like this is a stupid question, but why are you comparing against optical flow instead of like tracking methods?
So, yeah, that's going to be my next sentence. Okay, at the time, this is now since changed, but at the time, if you wanted the best performance on tracking in the state of the art with supervised data, it is kind of off the charts here. Okay, but what did that require, right? For the state of the art tracking, it required ImageNet, it required UMass Coco, they even train on the testing frames, right? And that's what gives you the best performance. So here the point was not to try to compete with the supervised models, because that requires so much data, right? It requires millions of labeled examples. This, in contrast, requires no labeled videos and just a single reference frame.
Is that FlowNet?
Optic flow here is.
But FlowNet's a supervised method, right?
That's right. So here we're outperforming FlowNet, which is trained on flying chairs data set, right?
Right. I mean, there are better things than FlowNet, right? Like energy-based methods that actually require less training data.
Right. So I want to make us, we're not claiming to have the state-of-the-art performance in tracking. There's something follow-up work though from Berkeley that adds, it's from Berkeley and it's another follow-up work from Andrew Zisserman, where essentially they combine this colorization loss with cycle consistency loss. And that actually does outperform state-of-the-art supervised models on this data set.
So Colin, I had a slightly different version of optical flow in mind.
Okay.
Because use the optic flow to supervise your embedding model.
Oh, but how do you get the ground truth flow to supervise it?
So yeah, use something off the shelf, noisy optical flow.
Sure.
Because
Yeah,
then you could use color to learn embedding of your patches.
Right. Yeah, that's something you
So there was this other paper that I saw. It's called Learning Correspondence from Cycle Consistency.
Yes.
That I think does something similar. I mean, you're using color, they use actual correspondence.
Yes. So, right. I think that's the Berkeley paper was referring to. They, what they do is tracking with cycle consistency. They show that it actually beats this, right? so anyways, we break down the results. Let me go to the next thing. So one sort of interesting visualization here is you can take these embeddings which are learned and project them down to lower dimensions, try to visualize what the embeddings learned. This visualization can be a little misleading because it's a many-to-one mapping, right? What this means is so you produce 64-dimensional embeddings which you project on 3 dimensions and visualize as a video. And so what's interesting is that objects tend to be clustered in this space. Because this dog shows up in green, that suggests that these embeddings are close to each other. Okay. And then the other interesting thing is that I think this kind of makes sense is that the two tasks are correlated. So if one fails, then the other will fail. So if it incorrectly predicts color in the video, it'll also incorrectly track that object, which I think is interesting because that suggests that if you improve colorization more, then you should get better tracking. Okay, I want to move on to the next thing, which is, I think what's exciting about the video to me is just the amount of realistic context that you get. And you don't just have pixels, but you also have sound in video. We can use sound to learn in unsupervised way, right? Vision and sound are going to be naturally synchronized. Whenever you interact with the world, right, you're going to have motion, but there's also going to be sound in the scene. And so this is some older work, which was basically trying to do, instead of learning to recognize objects from images, can you learn to recognize objects from sound? And so the task here is given a waveform, can you solve a classification task of what objects or scenes are active as part of it. This is there's a whole corresponding community of computer vision and sound recognition. This is a hard problem. What we wanted to do was take advantage, a very simple idea, is just take advantage of the natural synchronization in video between the two modalities and use vision as a teacher for the sound modality. And so if a visual model can recognize that there's a lion here, that provides free supervision in sound in order to teach a student model in sound to do recognition. And so you can set up just a very simple loss function where you minimize scale divergence or whatever you want between a student model that operates on waveforms and a teacher model that's already trained to do recognition in vision. So we created a convolutional network for sound. To do this, the previous state of the art at the time for sound recognition was this 4-layer convolutional net. So not very big. We created SoundNet, which is an 8-layer convolutional net. And essentially, it's a convolutional net that takes in just waveforms, which is a 1D time series, and produces a distribution over the categories. Okay, I guess what's interesting about this model is that even though it's never seen a labeled example for sound, it's seen labeled examples of images, but it's never seen a labeled example for sound. It can recognize objects and scenes from sound. So I thought what I'd do is I'd play some of the sounds and see if you can recognize what the objects are and scenes are better than SoundNet. Sound's a hard modality. It can be harder to do recognition. But so play a sound. Think of what object and scenes there could be from the sound. What do you guys think?
No.
Dog. Okay. So here I'll play it again. This is and the video is going to fade in. However, the video is only for your benefit. The model never saw the video here. The top are the predictions from the model for scenes, and the bottom are the predictions from the model for objects. These are image categories. These are places categories. Video. person, but if you Google English Springer, it looks a little bit like this dog. I don't know if it's possible to recognize dog breed from their bark. It seems like it might be, but I'm not claiming that. But it's
How many different dogs were there in there?
There are quite a lot. This is ImageNet. ImageNet has 50 different dog categories. So it is. Okay. Right. So, but it doesn't. What's interesting with the model is it doesn't just recognize the object, right? It's also background noise. It tells you about the space, right? You hear wind, right? And that tells you a little bit about the scene. It tells you, for example, you're probably outdoors. Okay. Here's another example which I like. Think of what objects and scenes there are from the sound.
Happy birthday to you.
So what's interesting about this is that the model produces a candle, which doesn't make sense because candles don't make sound, right? But it's trained on so much video. It's trained on 2 years of video here, and so we're in this spurious correlation, right? That the happy birthday tune means that there's going to be a candle.
Dear Gordy, happy birthday to you. Ready?
Okay, so I don't know. I think it's worth repeating just how it hasn't. I mean, it's just all the cross-modal context between vision and sound, right? Is you can get at such huge scales, and it really feels like this research we should continue to leverage. So you can evaluate this on standard benchmarks in sound recognition. In the original paper, we evaluated on 3. I'll show you just the most challenging one. This is a task where you're given a waveform and you have to categorize it in 50 different categories. Chance is 2%. Human consistency is 81%. So it is hard for people. Right? At the time, the previous state-of-the-art was CNN. They got 64%. If you train, and so what our approach got was a 10% gain, which was 74%. And so this is quite a large gain, I think. It's a little unfair because we had access to so much more data, right? We had millions of examples, while they had tens of thousands of examples. But at the other hand, right, the data we have is unlabeled. So then this is showing the advantage of using unlabeled data. There's since been follow-up of work for Andrew Zisserman's group, where they co-train both the vision and the sound classifier. And I think they can show that they actually match human consistency on the data set. So not to say that sound recognition is solved, but that data set is now is solved, and so we need more challenging data sets for sound. Okay, just some interesting visualizations here. We can look at the TSNE and embedding between a visual classifier and the sound classifier. The colors here are corresponding to different scene types. And so vision's a much easier domain, right? It's easier to determine scene type from vision, so these clusters are more well defined in the visual domain. In the sound domain, you still get some separation. What I'm really excited about this direction, something we're trying to set up now, is using sound for situational awareness. So you think about how much power it takes to turn on a different sensor. A camera is actually pretty expensive to turn on. Right? Microphone is very cheap to turn on. So even though it's not as accurate to do recognition from sound, it requires much less power. So you can do situational awareness on a wearable device, or you put microphones all over them. Okay, so on this model, we've done some, because it's trained on so much unlabeled video, we're interested in trying to understand what does this learn. And so we do have all the standard visualization tricks that we have in computer vision, but apply them in sound now. Because it's a convolutional net, for the very first layer, we can look at just the weight, we can look at the convolutional filters, right? And this is 1D, and so these are the first convolutional filters for the first layer. It's not too interesting, it kind of learns these different detectors for different frequencies. What gets more interesting is as you go deeper into the model, we try to understand what is the representation you're learning. The way we do this is this now standard trick where you pick a unit inside the model and you feed a bunch of images or sounds, in our case sounds through, and see what sounds activate your unit the most. Right? It's not a perfect visualization, but perhaps it can give us some intuition. What's interesting is that the model automatically learns some units for different atomic sounds. There's one unit that responds to smacking sounds. Sounds like this. Smacks. There's another unit that responds to chimes. But what's pretty interesting is you go deeper into the model, it starts to compose these atomic units into more higher level detectors. And it's not that surprising because we're getting closer to the categories of train and predict. So you can find these units in the model. So you find a unit, for example, that responds to, it tends to respond to people who scuba dive and sounds of that. So it sounds like, it's almost like Darth Vader. My favorite one is it's a unit that responds to parents talking to their babies.
And then that help coming out.
Right, so because the data set we have is, it's these home movies that people upload. There's a lot of kids in these days. Okay. I guess I can quickly do this here. So, okay, the last step, which I'll just briefly mention, and this is what we with my co-authors presented at ICCB just last week, is that in video, another modality that we have is speech. And we've been interested in using speech as self-supervision to learn representation and vision. And so if you just, if you just take random videos from the web, and so here we took instructional videos, there tends to be narration on top of them that's describing what's going on inside the videos. Here's one example.
Here I have the red onion. You can chop vegetables however you like, but I usually like kind of cut into lengthwise for this soup, but it's really up to you. Alright, so that's the red onion. Put that on the side.
Okay, and so right, even though a lot of these words are not directly related to the scene, right, there is some signal there that tells us about what an onion is, what chopping is. I think what's interesting about this is that we can potentially tackle the long tail here at scale. So people upload all sorts of videos to the web, describing various things, and so, for example, people can talk about exotic fruits that you've not seen before.
And now here's where we're going to go in with the actual API that I read off earlier.
And what's that? What is that, right? But just from this, what's interesting about this type of data is that just from, you don't know what the word Aki means, but because you have vision as a modality of sight input, you can infer lots of things. You can infer that Aki must be a food, right? You can infer what typical colors it might be. You can infer that, well, this is something that you could wash, right? Or even about size, right? You know what it's probably larger than it's made of. So we're not quite at this level of reasoning yet, but I think this is one thing that's exciting about this type of data is when you work across you work across vision, language, and sound, the two can help each other. So this project, we can collect a bunch of videos that also have a speech in them. So we have 900 hours of video of people talking about there's instructions for cooking, and we can automatically extract the speech with automatic speech recognition. And so here's just what kind of speech stream looks like. Then what we're interested in doing is using all this data, and these two temporal streams that are synchronized to try to learn a representation for vision. What we did was we took the very simple, essentially here, is there's been a lot of work in NLP with BERT. Have you heard of BERT before? Okay, so I've about half the room. BERT is a very interesting model in NLP that is basically smashing a lot of benchmarks in natural language processing. Essentially, it's a language model, and we extended BERT to include vision too, where it's trained with the essential speech here that we can extract, and we also have the corresponding frames. And so we can create this transformer model where you input the speech and you input the frames. It does, what BERT basically does is pairwise attention between each token here. And you train it so that if you randomly mask out different inputs here, it has to recover that token. So in language, if you treat each word as a token, it's not discrete, so it's actually pretty easy to transform it as a classification task. In vision, vision is not discrete, right? And so the quick thing we did here, I don't think this is the ultimate solution, is we can quantize the visual space, turn it into tokens, so that when you train this to give them tokens, that's to predict the corresponding tokens here.
Did you think about just taking random patches, one of which is correct and others of which are incorrect, and just having to choose the correct patch?
Oh, yeah, that was no type of task you could do. So there's since been a bunch of follow-up work on visual language modeling. There's visual BERT, VII, and they explore different combinations of this. So this task, I think, is what's interesting about this task, when you have the two domains, right, is if you mask out the keyword stake here, right, what do you have to use to fill in that word, right? If you only have access to language, it's actually pretty hard. Place the blank in the pan, right? But if you have access to the visual stream too, you can infer, right? Well, there is this typologically hope it would learn, although it's hard to empirically show it learns this logic. Is you hope you can recognize, well, here's the pan and there's a stake in the pan. Therefore, this word should be stake. Okay. So anyways, you can train this up on all this data, and then you can use it for a couple of different tasks. So one task is prediction, where given just a input frame, we can try to predict what are the sequence of steps that could happen next. Right? And the way you do this is you take that same model and just unroll it. So you fill those in the blank and you keep feeding forward to commercial predictions. And so here's a kind of people putting a flower in a cup, right? And the next step it predicts is that, well, maybe this might go into another next. And then you get a tasty treat out at the end of the day as you go further out. There's some errors here, right? The cake here turns into a muffin, right? I think it goes back to this case of common sense somehow, where, right, we all know that cannot happen. Okay, here's another example where you eat eggs and it predicts kind of this possible sequence of steps. But because it's trained with language too, we can use it for different recognition tasks, where if you input a video sequence here, rather than having it, rather than reading out the predictions that temporally in the future, you can read out the predictions from this speech stream. Excuse me. And so, so the prediction from this speech stream from this input here is it can predict different words like verbs and nouns. It also predicts a bunch of spoken words that are not related into the scene, so we don't show those, but it is getting kind of a gist of the scene here, just from this noisy data of people talking about their events. it can correctly recall it as though lemming here, it makes a mistake on the two. Okay, here's more examples. Okay, so this is really just the first step here. I think there's a lot of interesting directions between here, especially about in terms of space and numbers. Right? So this is it's hard. In language, it's very hard to learn about space or learn how to count. Right? How do you know that 5 is greater than 4? Right? In vision, that's actually pretty clear. Right? You see four things, and then you see five things. That is clearly more. So I think what's interesting about this type of work is that by doing two modalities together and doing joint modeling, you can problems that might be easy in one domain can help out another domain where it's very hard. Okay, and so I'll just